Hello everyone! For the third time, we'll be working with a shader based on a line graph with many vertices. This time, we'll program an effect that loosely resembles a seismograph or another instrument with a similar display. It's a fairly simple algorithm and, as usual, comes with plenty of parameters to customize its appearance. So, let's get started. Originally, I wanted to call it an ECG, an electrocardiograph, but then I realized that a healthy person's heartbeat could never look like this. So a seismograph is actually a much better match for this kind of waveform. So without further delay, let's create the usual scene. So I'm right-clicking the scenes folder, create new scene, and it's going to be a user interface, and let's call it seismograph. Okay, now I right-click the root node and add child node colorrect. And in the inspector, I'll change its color to black, expand the layout transform and set the size to Full HD, 1920 by 1080. Okay, and scrolling down to the material section where I create a new shader material, click it and create a new shader type, shader mode canvas item, and let's put it to the shaders folder and create. And this time I usually say that I click it again to open in the shader editor, but it's already done, so it looks like Godot since the version 4.7 is doing that automatically. Great. All right, and as usual, I'll delete everything we don't need, leaving only the fragment function. So deleting vertex and deleting light. Control S to save. Okay, so let's start with the uniform parameters. This time I'll add most of them right at the beginning, since they are all required to render the basic effect. And as usual, the first parameter defines the resolution of the element the shader will be applied to, in our case, the dimensions of the colorrect. So, uniform vec2 resolution equals vec2 1920 and 1080 are Full HD resolution. Very well. Next, we have the speed parameter, which controls the animation speed. Its hint range will be slightly different this time because we want to be able to move the graph in both directions. So it will also include negative values. Uniform float. Speed with a hint range and initial speed are set to -2. Okay, and as I said, the hint range will go from -5 to 5 with the step point 0,1. All right, the next two parameters determine the shape of the resulting curve. I'll call them wavelength and amplitude. So uniform float wavelength. With a hint range and the initial wavelength, I think I set to 100, and the range goes from, let's say, 8 and to 2000, because we'll be working with real pixels, and the step is 1 in this case. All right, and the amplitude, uniform float amplitude, and the hint range, and I think the amplitude was 0.4. Okay, and the range goes from 0 to 0.5 and the step point 0,1. All right, the following two parameters define the line thickness and the amount of smoothing used when drawing the curve. It will be called line width and line AA. Let's add them. A uniform float line width with another hint range, and the initial width I think I set to 1.8, and the range goes from 0 to 10 with the step point 0, 1, and finally, not finally, but at least for this moment, uniform float line AA for anti-aliasing with a hint range, and the initial value is 1, and it goes from 0 to 10 again with the step point 0, 1. All right, and finally, this time we need to define the curve color and the background color. So let's do it here. A uniform float vec4 RGBA format, line color with the hint source color, line color uniform, sorry, not flow, of course, just vec4 line color with the hint source color, which means that the inspector will show a nice color picker to change it. And the initial value, I think I set to 0.2, 1, 0.4, and 1 for the alpha value, so it's going to be some kind of a shade of green. And the background uniform vec4 BG color, again a source color, and I think I set the default value to black, so 0, 0, 0, and 1. Okay, we use vector 4 because sometimes, for example, we would like to have a transparent background. So in that case, we'll just change the alpha to 0 and it will be transparent as we expect. Very well, we'll add a few more parameters later, but these are good enough for now. The last thing I'll insert before writing the code is a constant that will help us achieve a smoother curve for certain parameter combinations. So let's put it right after the uniform parameters, const int integer sample radius equals 4. You might be wondering why sample radius is not defined as a uniform parameter as well. It certainly could be, but I wanted to use a constant to demonstrate an optimization technique for certain parts of the code. I'll get to that very soon. Okay, so as you can probably guess, creating an effect based on pseudo-random values requires several helper functions to keep the code well organized. This time, I won't be writing these functions from scratch because it would only waste time, and I don't think it's particularly entertaining to watch me slowly type relatively boring code. So instead, I'll insert them one by one and explain what they do. Okay, and I think I can expand this window so we'll be able to see more of the code. Very well, and let's start with 3 short functions whose purpose is to generate pseudo-random values in the form of a smooth curve. They will look like this, and I am pasting that right after the constant and before the fragment function. Here it is. So what do we have here? The hash11 function, the first one, returns a value in the range from 0 to 1, while also taking a one-dimensional value as its input parameter, hence the name hash11. It's a simple algorithm that I've used many times in other tutorials. This generator forms the foundation of the noise function, the second one, which smooths the generated values using cubic interpolation, this formula, in much the same way as the smooth step function does. Finally, we feed this input, its output, into the FBM function, which stands for the fractal Brownian motion, an algorithm that is explained exceptionally well in the Book of Shaders, a free online resource. And as always, you'll find a link to it in the description of this video. So with that, we're ready to obtain the signal value that our final curve will represent. And this function is actually very short and simple, so I'll write it manually. Float signal add with the parameter float t And at this moment, it's just return FBM, return FBM of T. Okay, so for now, the signal add function is very simple. As I said, I simply return just output of the FVM function. Later, we'll enhance it by adding random spikes to simulate distant earthquakes. To draw a portion of the curve, we'll need a function which I'll call curve point. I'll write this one from scratch because it's simple as well and also makes use of several uniform parameters. Essentially, it takes the output of the signal add function and shifts it along the y-axis so that the graph is vertically centered. Okay, let's write it here. Vec2 curve point, the parameter float local x, because we are supposed to work with local coordinates which are represented by the pixels. And now the body float d is local x divided by wavelength, one of our uniform parameters. And since we want it to be animated, we need to subtract time times speed. Okay, and now the y coordinates, so float y equals 0.5. As I said, we want to shift it along the y-axis to center it vertically, plus amplitude, another parameter, times signal add, our function, with the parameter t. Okay, and let's multiply everything by resolution.y. Very well, and now we can return the result, which is simply vec2 local x and y. Cool. The only thing left is to reuse the code we created in the previous tutorial where we programmed a heart monitor simulation. First, we need the function that calculates the distance to the line segment between points A and B. Let's write it here. Float line segment with parameters vec2 B for the point, and now vec2A and vec2B. So the line is defined by these 2 points, everything in between. All right, and I'll just write again the same formula as you could have seen in the previous video. PA is P minus A, vec2 BA is B minus A, and float h, sorry, it's supposed to be equals here, float h equals clamp of, again, the division of two dot products, dot PA and BA, divided by, and now I'll use a failsafe because I'll get to that very soon. Dot of BA and BA and some small number 1e negative 6. Okay, and the clamping range is again 0 and 1. All right, and now we can, what exactly is not correct? I suppose dot, of course. And let's return the length of the resulting vector. Return length of BA minus BA times H. Okay, so as I said, I've added a failsafe using this max function, which means that the result will never be 0. because since the curve changes so frequently, some points could end up overlapping. And also, the Godot shading language doesn't crash when dividing by 0. It returns an NaN, which is short for not a number value, whose behavior isn't well defined, so it's much safer to handle it this way. And finally, I'll write the function that finds the closest curve segment for the current pixel. So let's write it here. I think it will be the last function which we insert before the fragment function. So let's do it. Float closest segment with the parameter vec2 uv. And now we are going to find the minimum distance to all related segments. So float min dist, as usual, it starts as some big number, 1e9, which is 1 billion. And finally, at the end, we will return it. But of course, it's necessary to do some other calculations as well. Okay, so vec2 previous point, because we are going to compare more points, and it's the result of our function curve point with the parameter uv.x minus float of our sample radius constant. It's necessary to cast it because the shading language doesn't do casting automatically, so we cannot just work with the float and integer. Okay, and now the cycle. So for int I from 1 I less or equal 2 times sample radius and I plus plus. Okay, and in the cycle we'll first calculate the offset, because it's always a little bit shifted for each iteration regarding the sample radius value. So it's float of I minus sample radius. Okay. And now the point vec2 b equals, again, curve point, and this time uv.x plus our offset. And finally, let's calculate the minimum distance. So min dist, new value, will be the minimum value of the previous min dist. And now the result of the line segment function with parameters uv, previous point, and our current point p. Okay, and let's reassign the previous point value to the current point p for the next iteration. Okay, and that's it. So this function uses the sample radius constant to repeat the algorithm inside a loop. As I mentioned earlier, the optimization comes from the fact that the compiler can unroll this loop into a sequence of repeated instructions, which can be particularly beneficial on mobile platforms. However, this optimization only happens if the loop definition uses constants, I mean this definition, exclusively, which is precisely why sample radius is defined as a constant rather than a uniform parameter. With that, we are done with the helper functions. I know this part of the tutorial wasn't the most exciting, but without it, nothing else would work. I think it's better to spend at least a few moments explaining the code than simply pasting it in and asking viewers to copy it as it is. And now we can finally move on to the fragment function, where we'll render the final effect we've been working toward. Okay, I think I can just collapse this window, because now we are very close to actually see something and the 2D editor will come in handy. So the first thing we'll do is convert normalized UV coordinates into actual pixel coordinates using the resolution parameter. So instead of this command, let's write this vec2 UV equals UV in capital letters times resolution. Okay, this time there is nothing symmetrical about this effect, so there is no need to shift the coordinate origin to the center. Next, we'll calculate the distance to the nearest segment of the resulting graph. Since the closest segment function, this one, operates in pixel space, we'll pass it the new UV vector as its parameter. So float min_dist equals closest segment of UV. Okay, now we can calculate the line we want to render. To keep it nice and smooth, we'll use the smooth step function with its edge values determined by the configured line thickness. So first I'll calculate half of that thickness. Float half width equals line width per parameter times 0.5. All right, and then let's perform the calculation using the line AA parameter, which controls the amount of anti-aliasing. Float line equals 1 minus smooth step of a half width minus line AA a half width plus line AA and min_dist as the weight factor, I mean the value. Okay, and the only thing left is to render the final pixel by blending the background color with the line color, like this. So the output, color in capital letters, equals mix of BG color, line color, and our line value. Wait for it, and here we go. At last we can actually see something, and I would say the result looks pretty good. Now we can experiment with the different parameters and see how they affect the appearance of the graph. So let's find them in the inspector, and for instance I can of course change the speed. Now it's in the opposite direction and faster, or I can stop it completely by setting to 0. Or we can change the wavelength, like this, or like this. Let's fix the amplitude. Now it looks maybe more like a seismograph. Okay, the line width can be, of course, higher, so the line is thicker, and the AA, it's actually much better visible if we just stop the motion and zoom in. And now if I change the line AA, yeah, this is zeroed out. Now it's set to a higher value. I think you can spot the difference. Okay, let's just get back to the original zoom factor and reset all parameters. Okay, so what else could we improve? It might be a good idea to add occasional extreme values to the signal to indicate that some kind of anomaly has occurred, for example, a distant earthquake. So I'll add two new parameters, which I'll call spike chance and spike strength. Okay, and again I expanded this window and I'm scrolling up to the uniform parameters section where I add these two lines, uniform float, spike chance with a hint range, and the value would be, I think, 0.9, and the range goes from 0 to 1 with a step point 0.1. Okay, the spike chance parameter actually works in reverse because a higher value means a lower chance of a spike occurring. And the second one, uniform float, spike strength, with a hint range and the initial value 1.5, and this range goes from 0 to, let's say, 4 with a step point 0.1. Okay, and now I'll go back to the signal at function. Here it is, which is now very simple, but we will improve it a little bit. I mean, not now. First, I need to add a function that is not there yet. So let's do it right before that, and I'll call it quake spike. Float quake spike with a parameter float x. Okay. And we will simply use the noise function several times and formulate something like a spike with a certain probability that it occurs. So float n equals noise of x times 0.35 plus 100, just to give it another seed for the pseudorandom generator, times 0.5 plus 0.5, which remaps the range -1 to 1 against 201, I think. And now float, let's call it burst, equals smooth step of spike chance, our parameter, and 1 and n, the new variable. The next line, float shape, equals again the noise function and another seed x times 4 plus, let's say, 50. Actually, the numbers don't matter too much. The important thing is that they are different, and let's return the result. Return burst times burst again times shape. Okay, again, a result of previous experiments. And now we can call this new function from within signal add. So return FBM T and plus quake spike of T times the second parameter, spike strength. Okay, and now if I adjust these new parameters in the inspector, we will see the graph respond accordingly, but of course we need to display it first. So where is it? Right here. So let's decrease, and now we can see the spikes appearing. Maybe they are too high, so let's just change the spike strength, but I think you got the idea. Yeah, there are definitely interesting things we can do with that, especially if I lower the amplitude. So now it could be even more interesting. Okay, definitely works. Let's reset. Very well. And at this point, it would also be useful to add a subtle horizontal line indicating the zero level, making the graph easier to read. So I'll add a couple of parameters to control this reference line. Let's again expand the window and scrolling up to the uniform parameters section and uniform bool, true or false. Let's call it draw baseline, so we can easily turn it on or off, and the initial value true, it will be on. And of course, it's supposed to have some color, so a uniform, again, vec4 baseline color with a hint source color, and the initial value, I think it was something semi-transparent, so vec3 1, yeah, white color, but with the alpha channel set to 0.2. Okay, and now I will insert new code into the fragment function. Let's scroll down, and since we are now blending a few more elements together, I'll also update the final color calculation, this one, assigned to the color output variable. So let's find this line and do it. Vec4 color equals BG color at the start, the background color. And now if we want to add a baseline, if draw baseline is true, then let's mix it in. So float base dist, we'll simply use absolute value and smooth step for driving a horizontal line, equals abs of uv dot y minus resolution.y times 0.5. Again, we want to center it vertically. And the line itself, float base line, equals 1 minus smooth step of 0.5, 1.5, and base dist value. Okay, and let's do the mixing. So color equals mix of color, baseline color, and baseline. And of course, we need to use its alpha value as well, so it blends better with the result. Times baseline color dot A. Okay, and if we take a look, there should be no change because we are still working here with the BG color. Let's change it to color. And there should be the line. Can you see it? I think if I just zoom in, it should be much better visible. Yeah, perfect. Okay, and the last thing I'll add is an adjustable glow effect for our curve. So I'll introduce two more parameters, and these are really the last one. I won't be adding any more after this. And again, I'll just expand the window and scroll up to the uniform parameter section. Okay, and the parameters are uniform float glow width with a hint range, and the initial glow is, I think, is disabled, so let's put it to 0, and the width can go from 0 to, for example, 60 with the step point 0.1. Okay, and the intensity of the glow, uniform float glow strength with another hint range, and let's set it to 1, and the range from 0 to, for example, 3 is a step point 0.1. Okay, and now we'll enhance the final color once again using the exp function with a negative argument, which is our favorite smooth out function. So just before this, the final color assignment, let's do it. Float glow equals exp of negative and bracket min dist times min dist, yeah, divided by bracket glow width times glow width. Yeah, I think it looks better than if I just use these values without multiplying them with themselves, like the power of 2. Again, something I've been experimenting with. Okay, and before I write the last line, let's just collapse the window so we can observe the result. Actually, we won't be able to because the parameter is set to 0, but let's get ready anyway. And color is increased by line color times glow times low strength. Okay, and now let's try adjusting these new two parameters in the inspector. So increasing the glow width, and it's definitely glowing, and if I increase the strength, it is even changing the color, like it's too intense. And yeah, I think we can create very nice combinations of the final graph we want to achieve. Of course, we can also experiment with all other parameters and fine-tune the effect to match exactly what we want, but I'm sure everyone can do it on their own. Thank you very much for watching. I think this is a pretty useful example of drawing a graph based on pseudo-random values, and with a few modifications, we could adapt it to generate curves from virtually any kind of calculation. We'll probably save that for another time though, because this video has turned out to be a bit longer than I originally planned. Until then, Take care, good luck with your game projects, and I'll see you in the next video.